Hello, everyone. Welcome to this week's TAIL seminar. So if you know me, I just joined SoMAS a month ago. So I'm currently a research scientist. Well, I actually got my PhD here about 4 to 5 years ago. So probably some of you still know me. So for this week's seminar, actually, Professor Edmund Tan should be hosting this, but he's now having another meeting, so I will be introducing the speaker today. So we have Dr. Shan, who joined SoMAS. Let me take my notes. Who joined SoMAS last November as a senior postdoc associate. So for Dr. He got his bachelor degree in applied meteorology in Shan University in 2015. After that, he continued in Shan University as a PhD student. During his PhD time, he also had a one-year visit in UC Irvine. He got his PhD in 2020, and after that, he became a postdoc in Shan University up until he joined SoMAS at the end of last year. Dr. He got several scholarships during his time as a bachelor's degree student and a PhD student, and he's also leading a few research projects, co-leading research project when he was back in China. He has quite a few publications with more than 6 first author papers, and his research interest includes ENSO, the mechanism for transition of different type of ENSO impact over the atmosphere and the ocean, the ENSO influence on atmospheric teleconnection. And also a major part of his work is about identifying and quantifying causality or causal relationship in the Earth system, which I think is related to this talk today. So the floor is yours. Take it away.
Thank you, and it's my honor to be here to talk about something about today. I will talk about inferring the causal structure to analyze, model, and predict climate variability. First of all, when we discuss causal relationships or causal structure or causalities, we here will refer to a model of describing the relevant features of the world and how they interact with each other. And that is a causal structure or the causality will describe how nature assigns values to variables of interest. And in Earth system science, we mainly establish causal relationships by the experiments. However, experiment sometimes is not available or not an option. For instance, for large scales, we cannot force sea surface temperature to study their impact, or the cost might be very large. So in this case, we only can establish causality from the observation. So the question is what method or what theory we can rely on to establish the causality in our world, and how. So in 2011, Herms was awarded permanent award for his contribution to the AI through the mathematical frameworks of the causal reasoning. And in 2021, 2 other scientists were awarded by the Nobel Prize for their contributions on the methodology to analyze the causal relationships. So to date, based on their contribution to to the causal theories and other scientists, I will develop my talks. And start by I will give you brief introductions of the causal theories, and then I will turn to how we can apply causal theory to study our climate system or Earth system. And I will conclude my talks by introduce more about what we can achieve by causal inference in a broader perspective. Currently, when we do research, we want to establish causal relationships mainly based on the associate-based networks, such as the low-dimensional associations, like linear correlations or something. But for this method, it cannot show. It only show the association, but cannot establish the causality. So let's consider these examples. We have three methods. The first panel show the linear correlations. The second show the low-dimensional gender method, and the last one show the causal structure method. So we can see that if we use the linear correlation, we can have a very high true positive to discover our causal relationships or the physical method or physical pathway. However, it cannot limit its full positive that we will discuss some result that do not work in our reality. And when we turn to the Granger method, we can see the x-axis represent the variable number. So when the variables increase, the performance of this method will drop dramatically, although it can limit the full positives of the results. However, when we use method based on the causal structure of the causal relationships, we can achieve very high true positive when we do research, when we limit the full positive, so that we will truly discuss our nature physics. So one reason why the correlation will cannot establish causality is that it cannot distinguish the correlation induced by the common causes. However, when we use causal inference, we can distinguish these common causes from the indirect causes and the direct causes. So based on the result from the correlation, we can build some model which are non-causals, or maybe the model will exclude certain common causes. So this model cannot predict climate very well when the climate change, such as the environmental changes or the sea surface temperature changes, or amongst others. However, if we use the result inferred by the causal inference, we can build some model which can reach the accurate predictions when the climate change. So consider this example. So this figure given that this figure represents our ground truth in the forms of the linear Gaussian assumption. So we can observe the x variable, the 4 x variables, and we would like to predict the y variable. However, we cannot observe the I variable, which can represent the climate change or other things. So we compare two methods. One method is the multi-regressions method represented by yellow dots, and the other is the causal inference method represented by the blue dots. So this figure shows the testing result. That is, we try to use both methods to fit our data to see whether they can fit the data very well. So both methods can fit the data very well. However, when the climate change, for instance, when the eye change, maybe have the distribution shift or distribution change. So we would like to predict why. We can see that the result from the statistic method find themselves pretty biased. However, the result from the causal structure can predict some unobserved environments very well. So one result is that for our statistic method, our method will select X4 as one of their informations to input, so that it will influence its projections. However, if we infer the causal structure from our data set, we will only use X2 to predict our Y, so that after the change of the environment, we can also reach accurate predictions. So this is why we would like to use causal inference compared with the statistic method, because it can achieve accurate predictions. So in addition to the advantage I previously mentioned, what we can use causal inference to achieve. So in our atmospheric research or other disciplines, what we can achieve by using causal inference. So here show some example. If we have data, or maybe large data, we can infer the causal structure so that we can generate or test our physical hypothesis, as shown in this figure. So after we have the hypothesis or the complete causal structure, we can quantify the causal effects of different mechanisms or different pathways, so that we can have the relative contribution of specific process. Yeah. In addition, if we have our causal model, we can predict our future. So for example, if we knew something, we can predict our future. Also, if we know the results, we can diagnose the causes of these results. Because we have the complete network, we can model our climate or the variable of interest, so that we know how our variables interact with each other and their statistic feature. Lastly, if we can infer the structure of our world as well as the structure of the model, we can compare their causal structure, and then we can evaluate how the model performed and their physics and something else, so that we can inform our modeler how to develop based on the result, whether the model can capture a specific pathway or their magnitude of the specific pathway. Before I turn to my study, I will give brief introductions of the causal theory, so that you guys will know what exactly causal theory can do, or how it do it. So to represent a causal structure, we usually use graph. In a graph, we use nodes represent variables such as node Y, node X, and node Z to represent the variable of interest, such as the ENSO, NJO, or the sun or something, or the earth. And the directed edge represent the causal relationships as shown in this figure. For the theory, our goal is to try to infer their direct causal relationships instead of their indirect relationships. So in this figure, we will have causal relationships between x, y, and y and z, but we will not have the direct causal relationship between x and z because y will mediate their causal effect. Yeah, in this case, we can facilitate the sparsity and we can estimate the mediations. And there's some important feature we should note about the causal inference. That is the directness is defined related to variables include. So take this figure for example. If we only observe the month and the floodings, we can say that the direct process of flooding is the monsoon month. However, when we include more variables, such as we can observe whether it rains or not, we can say, oh, in this situation, the direct cause of the flooding is rain, and the direct cause of rain is the monsoon month. However, the monsoon month is not the direct cause of the flooding. So this is one feature very important when we include more variable. It will change our structure. Another feature is that causal effect is probabilities. That is, for instance, in the terms of linear regression, it will take the terms of the linear correlation coefficients. So we can have a certain degree of belief whether something happen will influence other things. And then we would like to know how to infer the structure. Basically, there are two steps. So first is to extract the target variable as a node, so that we can represent our variables of interest in the structure as the nodes. And then after we have the variable of interest as nodes, we can learn how they interact with each other by learning their causal structure. And the basic idea is that to try to remove their edge or their connection between two variables if these two variables are independent after condition on the third variables. So after remove the potential connection, there are some connection remained, and we can regard that as the potential causal connections. So this is the step one, as shown in this figure, is to remove the connection as many as possible based on some algorithms I will not discuss in this talk in detail. And after we have the structure of the framework, we would like to originate their directions. So there are also a lot of procedure out there to originate their edge. So in this study, I will only use the procedure of the time order. So the cause come after the effect. So, and based on this, we can originate the edge. So this is the step 2 as shown in this figure. Let's take this figure as an example to see how we can obtain the causal structure for our data. Suppose we have 4 variables of interest, and figure D represent the ground truth in the forms of linear Gaussian assumption. So we start with a fully connected network. So that is each variable connected with each other. The first step is to remove the connections. As I said, this ground truth is follow the linear Gaussian distribution. So we can use a linear regression to remove the connection in this case. So the first step, we can see there was no correlation between X and Y. So the first step, we can remove the connection between X and Y. And then we try to fix a variable such as we fix J. After fixing J, we can see that X and W and Y and W can find themselves independent. So we can remove the connection between X and W and X and Y. And then we have this structure, and we can originate their directions by some procedure. So we can finally have their structure as shown in figure D. So this is an example how we inferred causal structure from the framework. Actually, we can use different mathematical assumption. If, for example, if we base on the nonlinear relationships, we can use other correlations to measure their connection. Finally, we have the structure, and we would like to know their causal effect. So there was a formula that well-established formula that we can have the specific causal effect of specific pathway. So this is the general introductions of the causal theory. After that, I will show how I infer the ENSO large-scale causal structure to facilitate the modeling and the accurate predictions of ENSO. By doing this, the result will demonstrate we can use causal inference to uncover the physical process that we do not know to explain or model or predict our large-scale climate variability or other variable of interest in other disciplines. Also, in the future, we can evaluate model simulation in the terms of their physical pathway because we have the structure, and then we can inform the model development and constrain the projection because we can see which model perform better than other models, so we can select this specific model. As I mentioned previously, the first step is to extract climate modes as nodes because I will focus on ENSO. So the variable I focus on is the sea surface temperature, the sea level pressure, and the winds over the tropic, and this is the warm water over the tropic. So the method I use is the rotated PCA to extract climate mode. In this figure, different colors and different number represent different modes. The spatial pattern of the different component is trapped from this method. So we can see the method can extract most of the component cover the global variables. So it can have a greater belief that we will not violate the no observed confined assumption. And then using the variables we extract, we try to infer how they interact with each other. The method I use is the PCMCI, and I won't describe it in detail. And if you want to know more, you can refer to this article. And I will focus on the time lag of 1 month because most large-scale AS interaction will lay on this time lag. And I will start with the linear Gaussian assumption in this situation, but later we can assume nonlinear models. And because the variable are quite large, so we also would like to increase the performance of the high dimensional variable selection by bootstrapping our causal result and then aggregate the result to select the link happen in the results most frequently. So let's turn to the result. Here I show a partial result of our structure. So this is just one part of our causal structure related to ENSO. Let's see the component number 191 and 114. So component 1 represents the Eastern Pacific mean sea surface temperature variation, and the 91 represent the Central Pacific zonal wind, while the 114 represent the east-west transportations of the warm water. So we can see that the gray scale represent their memory or the auto-causal effect. So we can see for the ocean component 1 and 114, they represent the ocean component. They do have a strong initial memory by using the causal inference. And then we can see the connection indicating a causal effect. We can see that the atmospheric component receives stronger causal effect than the oceanic component. So this feature capture our initial memory in our world. That is the causal inference can capture some physics feature in our world. And then let's see this three component form of positive feedback. That is when there is sea surface temperature increase in the sea surface temperature, it can increase the westerly wind, and the westerly wind can transfer water towards the eastern part. And then after there is eastward transportation of the warm water, the warm water accumulate over the Eastern Pacific, and it can increase the sea surface temperature in turn. So forming the positive feedback, that is the BJ feedback of the ENSO. And then let's turn to the component 114 and 117. So the 114 represent the transportation of warm water eastwards, and the 117 represent the warm water over the Pan-tropic ocean. And it also represents the transportation of the warm water from the tropic towards the extratropic. And we can see these two variables form negative feedback. That is when there is warm water accumulates in the Eastern Pacific. There is polarwards transportation of the tropic warm water by the geotropic currents. So decrease the tropic warm water. That is decrease the component 117. After this decrease, it can reduce the eastward transportation in the tropic. So forming the negative feedback, and that is the discharge oscillator of ENSO. So these two results demonstrate that the framework, our causal framework, can capture our physical world. That is, it can capture the ENSO mechanisms, the positive feedback and the negative feedback. So as for other structure, I won't discuss them in this talk. And if you guys are interested in it, you can study more about it. And then we have a causal structure, so we can try to see whether it can manage to predict and simulate our world. So based on the causal structure, we infer the whole causal structure, not just the causal structure I present just now. I construct a linear Gaussian model to predict our world. So here show the simulation result. That is a free runs of the model in the forms of linear Gaussian. So this is the tropic Pacific sea surface temperature variation, and we can see this result. It can simulate the ENSO because the ENSO events varies in their magnitude in this figure, and not only the magnitude but also the maximum location. We can see there was Central Pacific ENSO and the Eastern type ENSO, and also the evolution pattern varied. We can see there are multi-year La Nina in the simulation. Also, there is a cycle event such as El Nino follow and La Nina event. So the model can simulate the ENSO diversity, which resemble our observation, and we further focus on the maximum sea surface temperature. So this figure shows the location and magnitude of the maximum sea surface temperature, and we can see that the location have a bimodal distribution that is in peak over the Eastern Pacific as well as the Central Pacific, which match the statistic feature of our observation. And we can see the magnitude of the Eastern Pacific is greater than the Central Pacific type, which is also match our observation that Eastern El Nino have stronger magnitude than the Central Pacific. So this simulation tell us the causal structure can inform can construct some model that match the statistic feature of our real world. And the next step is we can try to see whether we can manage to reach prediction. So here is the result from the prediction. We just focus on the short time prediction. But if we would like to predict multiple steps, we just use the recursive method to predict the multi-steps situation. However, in the future, if we would like to improve the performance, we can construct a model with other prediction method, not only the recursive method. So here we can see this is for the 1 month lead time prediction. That is a direct prediction. No need to use the recursive method. The pattern resemble to the observation. And when we turn to the multi-time steps predictions, here show the 6 months lead time prediction. The pattern also resemble to the observation. That is, it can predict our ENSO feature quite well, although the magnitude decrease a little bit low. So this is the performance of different prediction. As we can see, as the model integrate itself, that is the lead time increase, the performance decrease. That is because the Gaussian, we assume earlier, the Gaussian noise accumulates, so that can decrease the performance of the predictions. And we also try to predict our ocean only using the atmospheric data. So we exclude the oceanic data to see whether we can predict our future scenario by using a partial of the data with the model. So this model only use the atmospheric data as input to predict the ENSO, and we can see the pattern also resemble to our observation. And it implies that if we have our causal structure model, we can predict our future scenario without complete information. So we can also use this model to other research such as to see their relative contribution of specific component by only inputting this variable. So we can see that, oh, some event may be due to atmospheric because it can simulate, it can predict, and the model can predict the ENSO very well in some situation by only using the atmospheric data, but not the others. So suggest the other event might also rely on the Oceanic process. So previous prediction only focused on the observation observed. We also try to use the same model to predict some situation we do not observe to see how it can perform. In this situation, we try to predict predict the ENSO from one of the CIMIC-6 model from the historical simulation. The model I select is the Mirror-6 model, which can simulate ENSO quite well. So we can regard these predictions as unobserved prediction. And we compare our model result with a statistic model built by Markov model, which is the current model mostly used in the ENSO predictions. And we can see the pattern of our model resemble to the observation quite well, and the magnitude is larger than what the statistic model predicts. And statistic model cannot predict whether this event is Eastern Pacific times or the Central Pacific time, but our model can have some insight about what times of the ENSO will be. So here show the performance of our model compared with the statistic method, and the performance is greater than the statistic model in the observed situation. So here show the take-home message of our first part. The causal inference framework we propose is capable of revealing both the physical nature of our climate and the ENSO mechanism. And by encoding the causal structure, a model can make predictions of the variable we are interested in, even without complete information or in an observed situation. We also, based on the causal structure we inferred previously, try to study the joint impacts of ENSO on the Eastern Asian summer monsoon, and we find that the Eastern time ENSO have the strongest causal effect to the monsoon, and also find there was 3 other winter phenomena can influence the monsoon together with ENSO, such as the Atlantic subtropical high, the Arctic temperature, and the Eastern North American sea level pressure. And based on these causes, we construct a simple linear predictions model to predict the internal variability of the monsoon and compare with the other model. So the result of our model is indicated by number 2. So the performance is quite comparable to component 11, which is the European model C5, because C5, it has been reported that C5 is the best operations prediction model. So I compare our predictions with C5 and find that the performance is quite comparable. And here show the result of our model. It can predict extreme values without major biases of this value. And this is the take-home message of our second part. Even laymen can use our causal framework to reveal some of the causes of our climate phenomenon and form some prediction models. And before I conclude our talk, I would like to present what we can also achieve by using causal inference to give you a broader perspective of what we can apply causal inference to help our research. So here shows some example, the up-to-date example. As we know, individual study will establish a single mechanism or a few mechanisms, but we would like to know how this mechanism from different study obtained interact with each other or their relative contribution. In this case, we can apply causal inference to study how this pathway interact with each other to give us a complete perspective and also give up their relative contribution. After we have the structure, the causal structure, we can note exactly how a certain variable can influence our global network, or how the global network can influence our variable of interest. So this figure shows their average causal effect and their average causal effect received. For instance, we can see that the outer circle represents the impact. The impact of it, we can see ENSO have the greatest impact in our climate system, while the inner circle represent the impact they receive. The tropical northern Atlantic received the greatest impact, indicates the environment in this region might be easily influenced by the climate change or something. And this information can help us to help policymaker to decide their policy. And other disciplines we focus on is we would like to predict or simulate our system using machine learning or AI techniques. So by using causal inference before applying the machine learning, we can select some variable which are causally related to our target, and then we input this variable to our machine learning algorithm. In this case, we can increase the performance of the machine learning method. As shown in this figure, the blue dot represents the machine learning algorithms improved by the causal inference, while the machine learning only, the performance of machine learning only represented by the blue line. So we can see the performance really increased by the causal inference method. And this is the result from the simulation. We also use machine learning to form our periodization. So by using causal inference to inform the machine learning, we can limit our biases to simulate our climate system. So now I will conclude my talk today by saying the result show us the potentials to infer causal structure for explaining, modeling, and predicting climate systems such as ENSO, and by integrate with nonlinear or non-Gaussian model, in other multi-step prediction, we can establish full benefits in operational addition in our research study. So I will stop here and welcome for question. Thank you.
Yeah, so I'm focusing on those two conclusions you have. Because the major assumptions you had is you start with a good
Gaussian distribution.
and it's fairly linear, right? Before you get to causal inferences. And then that drives your system. So you really kind of bias the system to be linear.
Yeah.
And it's whatever you get is just being produced by the linear, but the non-linear interactions are being left behind.
Yeah.
How do you go back and take care of the non-linear interaction? Because we know that the system
is
climate system is
no linear.
very
Yeah, so the method to deal with this problem is use other model. As I previously mentioned, by remove the connection between two variables. In my study, I use linear relationships. So if you focus on nonlinear relationships, you can use other methods such as the information test or something that can deal with nonlinear relationships. So if your target is to focus on nonlinear relationship, you can turn to nonlinear task. And my talk start here is just start with the linear relationships. And as there are also whether we can obtain as many as relationships when we do not assume nonlinear relationship. And previous mathematical studies show that by assume linear model, we can obtain most of the relationships, although they feature some nonlinear, but they do omit a few of them. And also we can so in this study, so it is justified by our result because it can simulate our ENSO quite well, although it do not feature the asymmetry which is induced by nonlinear mechanism. And for the large scale climates, the relationships are mostly linear, but as you said, part of them are nonlinear. Yeah, but the contribution is not that great, so that we can obtain most of the relationships. And if we want to obtain the rest of them, we should turn to nonlinear assumption. Thank you.
Yeah, just sticking with this figure, right? Yes, I'm trying to understand the sample size issue, right? If you train your system, your causal related like the ENSO, and then you have to evaluate it. So how do you separate the training and then the evaluation for something like ENSO, which you have fairly limited events?
Yeah.
So maybe I didn't understand.
So here I only focus on the monthly data. So I just separate into 5 sets. Separated into 5 sets. So I test. Each time I use one set as the verification, and I change my model to the rest of the 4 sets.
Just a quick follow-up. I mean, I don't know much about causal structure, degree paper, I guess, but I'm trying to understand how, you said in the end that this can help machine learning. And there's a lot of effort, obviously, machine learning to just use like random forest or something to figure out those causal relationships and then ultimately improve your system. So I'm trying to figure out the value added here of your 2-step process and that versus just feeding some kind of machine learning neural network or something to get the relationships and ultimately a better forecast of the prediction. So I guess what is missing in like a random forest or that process that you are doing that machine learning can't figure out?
So to use causal inference before forecast, before the random forest, we can select the variable which are causally related. And as for the random forest, this method do not know which variable is causal related, and they just focus on the correlation and the association. So in this case, the result demonstrates by selecting the variable have the causal association, it can help the random forest to achieve a better performance by limits
I understand that, but in some sense, like with ENSO, we kind of know what those causal relationships are based on all the decades of research, right? So we can almost, we know the fundamental physics and dynamics. So so it'd be interesting to compare that kind of a priori knowledge with some system like that with like your approach to see, what you're adding. Because I mean, if I'm designing like a random forest, of course I'm not going to throw random variables in there. I'm going to pick ones that are physically relevant to that system, based on the literature and everything else that we understand. And that could be compared with your approach, which is maybe more objective or some quantitative where you could sort all that out. So that's what I'm trying to distill the difference here.
Yeah, sure, we can. So and also because this is we start with ENSO, and the causal inference not only do a good job in prediction, it also can provide us some physical hypothesis, which is advantage, and machine learning might not be able to achieve. Yeah, so I just say not only focus on the prediction, but also can obtain some physical hypothesis. And as you know, the ENSO is well established. We know the mechanism very well. We can try to apply the causal inference to other disciplines which have a lot of unknown questions. Thank you.
Just to add on what you just said, when you reduce the number of features, the number of variables, you reduce overfitting, you minimize overfitting. So what the causal inference does, it reduces the dimensionality.
Yeah, limits the overfitting.
So I think this is a very basic question because all of this is new, but it seems like causal inference that you have a bunch of regression relationships that you're trying to figure out, a bunch of correlation relationships, right? You're trying to figure out which ones are primary and which ones are not primary. I don't understand at all how the methodology works to go from just simple correlations that you tell through regression, or that you can figure out what the correlation is from a regression relationship. How does it pick out the causal relationships to get from just correlation to causality?
Yeah.
Can you?
Sure.
So I feel like that's what you talked about the whole time, but I don't know. Can you sort of briefly summarize?
Sure. So in my talk, I mostly focus on the linear relationships. So if we focus on linear relationship, we can use the linear correlation to investigate that. And for the causal inference, you have a lot of assumption. So we begin with there was no unobserved observation. That is no other variable will influence our structure. So we can finally obtain the final structure of this network by using correlation of the linear relationship. But as your question might will turn to some nonlinear model, which I won't cover in my talk. So they have other methods to see how their noise can transfer from one variable to another variable. And this transfer only take place when there is causal relationships, which do not cover in my talk. Yeah, so basically I cannot give you a brief describe because there are a lot of theory and topics. on these disciplines. Yeah, so just let me summarize that if we focus on the linear relationships and we do not have unobserved variable, we can obtain their structure by triangle their causal structure. Yeah, by triangle their linear relationships systematically.
I think in terms of determining the direction of the causal relationship, one thing is actually included here is when we are looking at these correlations or regressions, it's not just the simultaneous correlation and regression, it's also the lead lag.
There's a lead lag.
So when one variable is leading another variable, we usually assume that's okay. The leading variable is causing the lagging variable.
From the effect to the
Yeah.
cause later.
But I think if there's the simultaneous correlation is the highest, there's also methods to determine which is causing which. I don't remember the details, but there are also ways to determine the causal relationship there.
Yeah, and there are a lot of procedure to determine their direction when we focus on the same time. So I cannot describe in one single talk because there are different assumption and different perspective. Yeah, we can discuss it later.
Yeah, very interesting thing. With the PCA or the Varimax approach, help the model to reduce some redundancy in the variables, such as opposed to the model come. Then after you use the PCA, you help to reduce some of the redundancy, some are important, let's call it factors or modes as the variables model. Did that help? Did the PCA help you reduce the redundancy or help to reduce the number of the variables you use?
You mean how to reducing?
I mean, you use the PCA or Varimax to get the modes the variables. Did that approach help you to reduce the number of variables you're supposed to use, but reduce to a smaller number of variables?
So if we compare with the original data, is 2D data. So compared to the original data, yes, the answer is yes, because if we want to conduct also inference onto the original data, we will focus on different grid point. And after applying the PCA or some method, it can extract the feature, the common feature of the data.
Right, I understand that. We have an ENSO going on now. What's your model prediction if you want to do that prediction in the next several months? Will it decay or will it keep just like that? Or
Yeah, good question. I did not do the prediction at this moment.
All right.
Okay, so we can continue our discussion during lunch in Challenger, and also for graduate students who can meet with the speaker after that.
Thank you.